I did it again. So I need to go fix that. Edit source because I did a copy and paste. In fact, I'm going to pause the video and do that right now. I will admit one benefit to recording on Zoom instead of my phone is that I can pause the video without having to start a new one. Math 2414, Trigonometric Substitutions, Video 3, another example using sine. Let's work one more example and remember the motivation for our trig substitution, and then we will categorize this. In other words, in the next video, we'll say, when you see this is the substitution. All right, so we're going to integrate the square root of 9 minus x squared over x squared dx. You might try a standard substitution, but if you try an algebraic substitution, such as u equals 9 minus x squared, you're just going to run into a big old mess. Don't believe me? Try it, fail, then come back and watch what happens. In the previous video, our motivation for the trig substitution was based on the subtraction problem and the fact that it resembled half of a, we didn't need to make that red. Stop making that red. If it's red, it's red. We'll just leave it red. Anyway, the motivation for the trig substitution was based on the subtraction problem that was located under the square root. If we try the same thing here, let's think about the trig identity that we used last time. Last time, we had a 1 minus x squared, and we compared that to 1 minus sine squared theta. Because if it was 1 minus sine squared theta, that equals cosine squared theta. And so we took these things, equated them, and square rooted both sides. But that's not quite the situation we're in here because our subtraction problem starts with a 9. So how can we take something like 9 minus x squared and compare it to something like 1 minus sine squared theta? When the problem is we have a 1 instead of a 9. And the answer is to take that trig identity, or at least that trig expression that's part of the trig identity, and turn the 1 into a 9 by multiplying the whole thing by 9. If we do that, we get 9 minus 9 sine squared theta. So really we still have the 1 minus sine squared, it's just got a 9 thrown on top of it, so it's a little bit hidden. But by taking the trig identity that we're trying to capitalize on, multiplying by the correct number so that instead of a 1 we have a 9, now we can equate the pieces that need to match. We need x squared to be 9 minus, we need x squared to be 9 sine squared theta. Well, if we take the square root of both sides, we get x equals 3 sine theta. And again, this is assuming that the square root of sine squared is sine, but we'll worry about that later. That's assuming sine is positive. But that's the substitution we're going to use. We're going to use x equals 3 sine theta. So let's clean this up and then proceed. All right. Before we start differentiating and substituting and doing trig identities, let's try to get into the habit of drawing a triangle for this equation before we do anything else, because we will need that triangle to help us undo the trig substitution at the end of the problem. So really we need to do two things with this. The first thing we need to do is to figure out how to, figure out what dx equals. That's pretty easy. Dx is equal to the derivative of sine is cosine. So dx is equal to 3 cosine theta d theta. And remember, we don't have to balance any du packages because we're simply saying dx is going to get replaced with this. So we don't have to balance out something with its reciprocal back in the integral. But the other thing we want to do is we want to draw a picture for this substitution. And the easiest way to do it is to isolate the trig function. We divide both sides of the substitution by 3. We get sine of theta is equal to x over 3. In other words, we're going from our substitution to an equation that says what sine of theta equals. And now we just have to draw a picture that satisfies that. And honestly, this picture can be drawn without solving for sine of theta, but since trig functions are defined as ratios, sometimes it helps see through them if we actually have a trig function equal to a ratio. All right, so sine of theta is x over 3, but Sine of theta is opposite over hypotenuse. So we need the opposite side to be x, the hypotenuse to be 3. And in anticipation of needing the adjacent side, we could go ahead and do the Pythagorean theorem and get the square root of 9 minus x squared. You know what? I think in this one, I'll real quick show you where that comes from. Whatever the adjacent side squared is, whatever the adjacent side is, when we square it and add it to x squared, we get 3 squared. That's the Pythagorean theorem. But if we square the 3 to get 9, subtract the x squared over to get rid of it from the left side, and then square root both sides to kill the square on the adjacent, we get the adjacent side is equal to the square root of 9 minus x. And if you need to walk through the Pythagorean theorem to figure out that missing side, go ahead. But if you can see it, by all means, just write it down. And it's not a coincidence, that's the same square root that's inside the integral. Okay, so now that we've got our substitution determined, and again, in the next video, we'll categorize how to determine that substitution without having to match it to a trig identity, but you can probably figure out where the 3 came from in the problem. Let's make our substitution. All right. So every x would become a 3 sine theta. Now, each of these x's happen to be squared. So everywhere there's an x squared, we'll just square both halves of 3 sine theta. 3 squared is 9. Sine theta squared is sine squared theta. And on the bottom, we'll get the same thing. Sine squared theta. Now for dx, we get 3 cosine theta d theta. At this point, it's now a trig integral, but we're not ready to try to evaluate it because the whole purpose of the substitution is to clean up the square root and more generically, clean up the subtraction problem underneath. How would we clean up the subtraction problem? Well, let's just do it off to the side for a second. Remember, the motivation was trying to expose a trig identity, and the trig identity we're looking for is disguised with a 9. So if we factor out the 9, we get 9 times 1 minus sine squared theta, but 1 minus sine squared theta is cosine squared theta, thanks to a Pythagorean identity. So the radicand, the part under the square root, will become 9 cosine squared theta. So we've made that change. And if you do enough of these, you start being able to take advantage of that Pythagorean identity quickly by saying, oh, 9 minus 9 sine squared theta. That's just 9 cosine squared theta. And luckily, everything under the square root will square root nicely. So this, on the top, the square root of 9 is 3. The square root of cosine squared is cosine of theta. With the right restrictions on theta, you might want the integral sign. We have a 9 sine squared in the denominator. And we still have this 3 in cosine over here just waiting to do something. All right, let's see how this cleans up. All the constants will cancel because you have 3 times 3 on the top. And when I say top, because that 3 is over 1, you have 3 times 3 on the top, but together that's a 9, so those all cancel. And we have a cosine times a cosine on the top, so that'll be a cosine squared. So now the integrand is going to be cosine squared over sine squared, both of theta. Let's write that on the next page. All right, so here's where we are now. Let's make that square on the sine a little bit more like a 2. Okay, so now it's a trig integral, and we have to analyze it as such. It is a combination of sines and cosines, and normally we pick on the odd power. Neither of these are odd. We could use some power reducing formulas, but that's going to make a mess. Can't be afraid to try things like, say, oh, that looks like a quotient identity. Cosine of theta over sine of theta is cotangent of theta. But since they're both squared, then that will be cotangent squared of theta. Now at this point you might go, now what? But if you know your derivative rules, cotangent squared looks like the derivative of something, sort of. Recall that the derivative, that's d dx, I'm not going to let that slide. Recall that the derivative of cosecant of theta, well, if I'm going to say theta, I should probably say theta down here. Recall that the derivative of cosecant of theta is negative cotangent squared theta. Well, never be afraid to make mistakes because, as I said before, it doesn't matter how good you are, everybody will make mistakes. So how do we integrate cotangent squared? Well, we might take advantage of a trig identity. I wouldn't call it cosine over sine. That'll take us right back where we started. But maybe take advantage of another identity involving cotangent squared. Hey, squared, that suggests a Pythagorean identity. Cotangent squared is the same as cosecant squared theta minus 1 theta. Now, is that advantageous? Yes, because what I was thinking earlier, when I was wrong, I was thinking cotangent squared is the derivative of something. Well, it is. It's just not a derivative rule. But it's not a derivative rule. Cosecant squared is the derivative of something, sort of. Derivative with respect to theta of cotangent theta is negative cosecant squared theta. And so we can use that to integrate cosecant squared. It is off by a negative sign. That just means we can put a negative on both sides to get rid of the negative over there. That tells us that the derivative of negative cotangent theta is cosecant squared, which means the integral of cosecant squared is negative cotangent theta. And of course, the integral of 1 will just be theta. So let's do that. And if you're thinking, wait a minute, we just learned that in the previous section about trig integrals. I know. But it's a constant buildup of what we did before into what we did next. So yeah, if you're still working and learning trig integrals, I'm sorry, I have to take advantage of them and move forward. And I want to remind you, in the book we're using, this is actually in the same section as trig integrals. I think the section should be split in half, but what do I know? All right, so we've got an answer for our integral, except it's in terms of theta. And how do we fix that? Well, we go back to our triangle, which I'm going to copy on the next page. Our triangle, which was motivated by our substitution of x equals 3 sine theta, has x on the opposite side, 3 on the hypotenuse, and the square root of 9 minus x squared on the adjacent side, courtesy of the Pythagorean theorem. We can use this to help write our answer in terms of x's. Start with cotangent. Cotangent theta is the reciprocal of tangent. Tangent is opposite over adjacent, which means cotangent is adjacent over opposite. The adjacent side is the square root of 9 minus x squared. The opposite side is x. So negative cotangent theta, according to this triangle, equals negative square root of 9 minus x squared over x. Minus. Now, what does theta equal? Well, if you just need to know what theta equals, then you have to go back to the original substitution, which was x equals 3 sine theta. And you have to solve that for theta, which is actually pretty easy. Just isolate the trig function by dividing both sides by 3, and then take the arc sine of both sides, and you get arc sine of x over 3 is equal to theta. And that's what's going to take the place of the theta in our answer. Arc sine, arc sine of x over 3. Plus constant of integration, and we're done. I know I mentioned this to one of you in a message when you messaged me about the content. Right now, we're at the pinnacle of difficulty in this class. That is my firm opinion. That trig substitutions are probably the hardest thing we're going to do. Because you have to not only make the substitution, but you also have to evaluate the trig integral, then undo the trig substitution. In the next video, we're kind of categorize what happens so that we don't have to reinvent the wheel every